Let's talk about 3.1 translational kinetic energy in Unit 3 of AP Physics 1 Work, Energy, and Power. So, what is translational kinetic energy? Translational kinetic energy is the energy of motion of an object that is moving in a straight line. So the formula that you need to know is K is equal to 1/2 mv squared, where K is equal to the translational kinetic energy measured in joules. M is the mass of the object measured in kilograms. V is the speed, but is not the velocity vector measured in meters per second. And also, remember that because velocity is squared, that means the direction doesn't matter because the positive and the negative sign would always cancel out to be positive. Some things that you should know about kinetic energy is that it is a scalar. It will always be greater than 0, and it depends on speed being squared. And when speed is squared, it doubles the speed. And it also quadruples the kinetic energy. Kinetic energy also depends linearly on mass, and doubling mass doubles the kinetic energy. Also, if speed is equal to 0, kinetic energy is equal to 0, because an object at rest has no kinetic energy. And since V is squared, kinetic energy again is never negative. So let's move on to relationships with kinetic energy. So let's say that we take velocity and we double it. So if we double velocity, the new kinetic energy will be 4K. And the calculation for this is you basically take the K is equal to 1/2 mv squared, and instead of plugging in all variables, you instead substitute one. And then for the one variable that you want to measure the change of the change of that effect, you substitute that variable in, the value in. And then once you solve it, you get the result. And that is how much greater, that's the multiplicative, that's the multiplicative factor by which how much greater the new kinetic energy will be. So, same thing for if you triple the velocity, the new kinetic energy will be 9 times as great. Now and this is because velocity has a squared dependence when you relate kinetic energy with velocity. Now let's move on to mass. So for mass, if you double the mass, that means the new kinetic energy will be 2 times as great, as you can see from the calculations on the side, where you substitute 2 for mass and then 1 for velocity because that stays constant. And we're only measuring the change, again, of mass, not velocity. So it'll be 2 times greater. Kinetic energy will be 2 times greater. Same thing for tripling the mass. The new kinetic energy will be 3 times greater because when you substitute 3 for m, that causes the new kinetic energy to be just 3. And also you ignore the 1/2 because that is just a constant that you hold the same as well, and that will affect what your multiplicative factor will be. And that is just like for when you're actually solving. But when you're trying to find the multiplicative factor for which the new kinetic energy increases, you just ignore it. And then you just take that as a factor for the new. And that's because mass has linear dependence, because mass is not squared, it's just multiplied when you're finding the result. Now let's say that we, more complicatedly, double the mass and also double the velocity. This will result in the new kinetic energy being 8 times as great. And this is because if you substitute 2 in for the mass and 4 in for the velocity in the equation, the result is 8 times as great, ignoring 1/2. So let's talk about the different formula variants. So for number 1, we have kinetic energy in terms of momentum, P. So what's the definition of momentum again? It's just going to be P is equal to mv. And let's rewrite kinetic energy using momentum. So rewriting it, we get K is equal to P squared divided by 2m. That's formula you should know. And this formula is useful when you are working with a problem that gives momentum but not velocity. Problem gives momentum and not velocity. Or when you are working with impulse or collisions. That's important. Impulse or collisions. Now, for our second variant that you need to know is the kinetic energy difference and the work relationship. So, for this variant, this is for when if an object's speed changes from V initial to V final. So the formula is going to be delta K is equal to 1/2 mvf. Okay, let me fix this. My squared minus 1/2 mvi squared. So you're just finding the difference you're just finding the change. So this is essentially like the work energy theorem, which we'll see later. Now let's talk about the graph of kinetic energy. So in the kinetic energy versus V graph, we have if the curve is opening up as a parabola, then we know this is because kinetic energy is directly proportional to velocity squared. And also we know that the slope increases as the velocity increases. And this is just a description of the kinetic energy. It just grows faster at high speeds. Also remember that the kinetic energy remember that, okay, so that's for versus V. But kinetic energy versus V squared is going to be a perfect straight line through the origin. And also remember that the slope is equal to 1/2 times m. Okay, so let's continue with how is kinetic energy going to be used in AP Physics 1. So just remember that work is delta K. Work changes, and remember that work changes kinetic energy, okay? Changes kinetic energy. Also remember that kinetic energy, it trades. It's like they just switch with each other. Like kinetic energy becomes potential energy becomes kinetic energy in closed systems, okay? Also remember, according to conservation of energy, that K initial plus U initial is going to be equal to K final plus U final. Also remember that according to power, kinetic energy will change over time. Changes over time in relation to power output. In relation to power output. And also remember, according to forces and dynamics, the net force determines the change in kinetic energy. And remember, for collisions, let's also write it on the side. Collisions, you must compare total KE initial versus final. Okay, so work, potential energy, conservation of energy, power, forces, and let me move this over a little bit, and dynamics. Okay, and in summary, let's talk about some reminders that you should have. So again, remember that you only want the magnitude of speed because it is going to be a scalar, not a vector. Also remember that ke versus v squared graph is going to be linear, and the slope is going to be 1/2 m. Also, remember that work done on an object increases the kinetic energy. And remember, whenever you have calculations, convert grams to kilograms, which is the SI unit. Also remember that kinetic energy is always positive. Delta K is also but remember that delta K can be positive or negative. And if you double V, that does not mean that you are doubling kinetic energy, because kinetic energy is directly related to V squared. And remember, the kinetic energy formula is not the same as the momentum formula. Remember that specifically, an example for velocity scaling is that doubling V will quadruple the kinetic energy, and that for mass scaling, doubling m would only double the kinetic energy. Also, remember that for work, delta K, the change in kinetic energy conservation means that potential energy becomes kinetic energy, and that kinetic energy becomes potential energy. And remember that kinetic energy changes. When you increase V, kinetic energy will change quadratically. And remember that delta K is just Kf minus K initial. And that's it for this.